Close your eyes and imagine standing at the edge of everything. Behind you, the familiar glow of distant stars. Before you, an endless darkness stretching beyond imagination. That darkness is not empty. It is the universe. Tonight we journey through the greatest mystery of all. There is no test waiting at the end. No rush. No urgency. Just the slow unwinding of cosmic secrets to carry you gently towards sleep. The universe is everything that exists. Every star, every planet, every atom, every thought. All of it contained within a single word that somehow holds infinity. Tonight we explore this infinite expanse. From the smallest particles dancing in the void, to the largest structures stretching across billions of light years. All of it waiting to be whispered into the quiet of night. Tonight, let's drift off together while exploring 100 soothing facts about the universe itself. There's no rush here. No test at the end. Just soft words and quiet wonders to carry you into rest. Welcome to Drowsy Discovery. I'm glad you found your way here tonight. Perhaps you've had a long day, or maybe you simply enjoy falling asleep to thoughts larger than any single lifetime could contain. Either way, this journey is for you. There is something profoundly calming about contemplating the cosmos. It is so vast that our worries seem small by comparison. So ancient that our lifetimes are mere flickers. And yet somehow, we are part of it. So settle in. Let your breathing slow. And let the weight of the day drift away like starlight across the endless dark. The universe as we understand it began approximately 13.8 billion years ago. Not in an explosion spreading through space, but as the very beginning of space itself. Before that moment, there was no before. Time itself was born alongside matter and energy. Everything that would ever exist began in a state smaller than the smallest atom. And from that impossibly tiny beginning, the cosmos has been expanding ever since. Tonight, we will wander through this expanding vastness. We will visit the earliest light ever released. We will drift past galaxies older than Earth. And we will contemplate truths so strange they barely fit within the mind. But there is no hurry. The universe has existed for nearly 14 billion years. It can wait a little longer while you rest. Let us begin with the very fabric of reality itself. Space is not nothing. It is something. We often think of space as emptiness. A void between stars. A gap between galaxies. But space itself is a thing. It can bend. It can stretch. It can ripple like the surface of a pond. This was one of Einstein's great revelations. Space and time are woven together into a single fabric called spacetime. And this fabric responds to the presence of mass and energy. A star does not simply pull on nearby objects through some invisible force. Instead, it curves the spacetime around it. Other objects then follow the curves of that bent fabric. Gravity is geometry, the shape of the universe itself. And this spacetime fabric is everywhere. It exists between your fingers as you rest your hands. It stretches across the void between galaxies. It is the stage upon which all of existence performs. The universe is expanding, not into something, but within itself. This is perhaps the strangest fact of all. The universe is getting larger, but it is not expanding into empty space beyond its edges. There is no beyond. Instead, the space within the universe itself is stretching. The distance between galaxies grows not because they are racing away from each other, but because the space between them is being created. Imagine dots drawn on a balloon. As the balloon inflates, the dots move apart. Not because they are traveling across the surface, but because the surface itself is expanding. The universe works in a similar way. And this expansion has been happening since the very beginning. Distant galaxies are moving away from us faster than the speed of light. This sounds impossible. Nothing can travel faster than light. And yet distant galaxies recede from us at speeds exceeding that cosmic limit. The key is understanding that they are not moving through space faster than light. The space between us is simply growing too quickly to ever be crossed. Light from these galaxies, already traveling toward us, will never arrive. The space it must cross keeps stretching faster than it can travel. These regions of the universe have passed beyond a cosmic horizon. We will never see them. We will never reach them. They are lost to us forever, even given infinite time. The observable universe is only a fraction of the whole. Beyond our sight, more galaxies spin, more stars burn, more worlds exist. We simply cannot see them. The observable universe contains approximately 2 trillion galaxies. 2 trillion. That number is almost meaningless to the human mind. It is 2 million millions. 2,000 billions. Each of those galaxies contains between millions and hundreds of billions of stars. And many of those stars have planets. Some of those planets may have moons. The numbers compound into incomprehensibility. And yet this is only what we can see. The actual universe, the whole of it, may contain far more. Perhaps infinitely more. We are surrounded by vastness that defies imagination. The number of stars exceeds the grains of sand on all of Earth's beaches. Consider a single beach. The sand beneath your feet contains billions of grains. Now consider every beach on Earth, every desert, every grain of sand anywhere on the planet. Scientists estimate there are roughly 7 sextillion grains of sand on Earth. That is a 7 followed by 21 zeros. The observable universe contains an estimated 200 sextillion stars. Nearly 30 times more stars than grains of sand. This comparison is meant to convey scale. It barely succeeds. The numbers are simply too large for human intuition. Each of those stars is a sun. Many have planets. The universe is not empty. It is overwhelmingly full. Most galaxies contain a supermassive black hole at their center. At the heart of nearly every large galaxy lurks a black hole, millions or billions of times more massive than the Sun. These supermassive black holes do not wander through space. They anchor their galaxies, sitting at the gravitational center like a drain at the bottom of a cosmic whirlpool. Our own Milky Way harbors such a monster. It is called Sagittarius A star. It contains about 4 million solar masses compressed into a region smaller than Mercury's orbit. Despite their immense mass, these central black holes are tiny compared to the galaxies they inhabit. Yet they may have shaped galactic evolution in profound ways. Galaxies and their central black holes seem to grow together, linked by processes we are still working to understand. Galaxies come in many shapes. Not all galaxies are spirals like the Milky Way. Some are elliptical, smooth and featureless, containing old red stars. Others are irregular, twisted by collisions or gravitational interactions. Spiral galaxies have rotating disks with arms where new stars form. Elliptical galaxies are more spherical, often containing little gas for new star formation. The shape of a galaxy reflects its history. Collisions can transform spirals into ellipticals. Mergers can create irregular shapes. The universe is a gallery of forms. Each galaxy tells a story in its structure. Some galaxies are actively devouring matter. When gas falls toward the supermassive black hole at a galaxy's center, it can heat up and radiate tremendous energy. These active galaxies outshine their quieter neighbors by factors of thousands. Active galactic nuclei come in many varieties. Quasars are the most luminous. Seyfert galaxies are closer and easier to study. Radio galaxies emit powerful jets. The activity is not constant. Galaxies may flare up when fresh gas falls toward the center, then quieten when the supply is exhausted. Our own galaxy is currently quiet. But in the distant past, the Milky Way may have shone like a quasar. Light from the most distant galaxies has been traveling for over 13 billion years. When we look at distant objects, we see them as they were in the past. Light takes time to travel. The farther something is, the older the light we receive from it. The most distant galaxies we have observed sent their light toward us over 13 billion years ago. That light began its journey when the universe was young. When stars were fewer, when galaxies were still forming. By now, those galaxies have changed beyond recognition. Some may no longer exist. Others have merged with neighbors or drifted far from where they appeared. We see ghosts, ancient images frozen in time, snapshots of a universe that no longer exists. The cosmic microwave background is the oldest light in the universe. Before galaxies formed, before stars ignited, the universe was a glowing fog. It was so hot and dense that light could not travel freely. Photons scattered constantly off free electrons. But approximately 380,000 years after the beginning, the universe cooled enough for atoms to form. Suddenly, the fog cleared, and light was free to travel. That ancient light has been moving ever since. Stretched by the expansion of space from brilliant orange into faint microwaves. It fills the entire cosmos in every direction. When we detect this cosmic microwave background, we are seeing the universe as it was in its infancy. The oldest photograph possible. And remarkably, this light is almost perfectly uniform. Almost the same temperature everywhere. But not quite. Tiny variations in the cosmic microwave background reveal the seeds of all future structure. Slightly denser regions where gravity would eventually gather matter into galaxies. The blueprint of everything was already written in that ancient glow. The universe may be flat. We speak of cosmic geometry as if space could have shape. And it can. The universe could curve in upon itself like the surface of a sphere. Or it could bend outward like a saddle. Or it could be flat. Euclidean. The geometry you learned in school. Observation suggests that the universe is indeed very close to flat. Parallel lines remain parallel forever. Triangles have angles that sum to 180 degrees. This flatness is not a coincidence. It is connected to how the universe expanded in its earliest moments. A process called inflation stretched space so thoroughly that any curvature was smoothed away. We live in a cosmos that appears infinite and flat, a geometry so simple it almost seems unlikely. Most of the universe is made of things we cannot see. When astronomers measure the motion of galaxies and the bending of light, they find something strange. There is not enough visible matter to explain what they observe. Galaxies rotate too quickly. Light bends too sharply. Structures hold together too tightly. Something else must be there. Something invisible. Something that interacts through gravity, but not through light. We call it dark matter, and it makes up about 27% of the universe. But there is more. Something is causing the expansion of the universe to accelerate. The cosmos is not simply growing. It is growing faster and faster. We call this dark energy, and it makes up about 68% of the universe. Together, dark matter and dark energy constitute 95% of everything that exists. And we have no idea what they are. The universe we see, the stars, the galaxies, the planets, all of it amounts to less than 5% of the cosmic total. We are made of rare ingredients in a universe dominated by mystery. The universe may be infinite. Current evidence suggests that space extends forever. There is no edge, no boundary, no wall at the end of the cosmos. If this is true, then the universe contains infinite space, infinite galaxies, infinite stars, infinite possibilities. In an infinite universe, everything that could happen would happen somewhere. Every possible arrangement of matter would exist. Given enough space, even the most unlikely events become inevitable. This is a strange and humbling thought. We may not be unique. Somewhere, impossibly far away, another version of this moment may be unfolding. But infinity is difficult to prove. We can only see so far. The observable universe is finite, even if the whole is not. We may never know for certain. The universe keeps its deepest secrets well. The geometry of space determines its fate. If the universe has positive curvature, like the surface of a sphere, it is finite. Travel far enough in one direction, and you would eventually return to where you started. If it has negative curvature, like a saddle, it curves away from itself in all directions. Such a universe would be infinite and open. If it is flat, it would also be infinite, extending forever without curving back. Current measurements suggest flatness. But small curvature is hard to detect. We may be living in a slightly curved cosmos without knowing it. The shape of space is a question we can ask. One day, we may be able to answer it completely. The universe has no center and no edge. It is natural to imagine the Big Bang as an explosion from a central point. But this picture is misleading. The Big Bang did not occur at a single location in space. It occurred everywhere. Every point in the universe was the center. Every point has expanded away from every other point. There is no edge to the cosmos because there is no outside. The universe does not exist within a larger space. It is all the space there is. This is difficult to visualize. Our minds evolved to navigate landscapes with boundaries. The universe has none. Every galaxy is equally central. Every observer sees themselves at the middle. This is not solipsism. It is geometry. The cosmic horizon limits what we can observe. Light travels at a finite speed. The universe has a finite age. Together, these facts create a limit to how far we can see. The cosmic horizon is not a physical barrier. It is simply the distance beyond which light has not had time to reach us. Objects at the horizon appear as they were in the earliest epochs. Objects beyond it are invisible, not because they are hidden, but because their light is still on the way. As time passes, more light arrives. The observable universe slowly grows. But the accelerating expansion complicates this. Some regions are receding so fast that their light will never reach us, no matter how long we wait. The horizon is not static. It is a dynamic boundary shaped by both time and expansion. Black holes are regions where space-time curves so severely that nothing can escape. When a massive star dies, it can collapse under its own gravity. If the collapse is complete enough, the result is a black hole. A point of infinite density surrounded by an event horizon from which nothing, not even light, can return. The event horizon is not a physical surface. It is a boundary in space-time, a point of no return. Once something crosses that boundary, its future leads only inward, toward the singularity at the center. We cannot see black holes directly. They emit no light. But we can detect them by their influence, by the way they bend light from behind, by the stars that orbit invisible centers, by the radiation released as matter spirals inward. Black holes are not rare. There are billions of them in our galaxy alone. And at the center of most galaxies lies a supermassive black hole containing millions or billions of solar masses. They are the darkest objects in the universe. And yet they are central to how galaxies form and evolve. Near a black hole, time itself slows down. This is not science fiction. It is a measured consequence of Einstein's equations. Time passes more slowly in stronger gravitational fields. Near a black hole, where gravity is extreme, this effect becomes profound. An astronaut hovering near the event horizon would age more slowly than their colleagues far away. Minutes near the black hole could correspond to years elsewhere. At the event horizon itself, time appears to stop entirely from an outside observer's perspective. This is not an illusion. It is how space-time actually behaves. Time is not constant. It is woven into the fabric of gravity and motion. The closer you approach a black hole, the more your future stretches out. The more the rest of the universe ages while you remain young. Time is stranger than we ever imagined. Gravitational waves ripple through space-time when massive objects accelerate. When black holes collide, when neutron stars spiral into each other, when stars explode asymmetrically, they send ripples through the fabric of space-time itself. These gravitational waves travel at the speed of light. They stretch and squeeze space as they pass. Everything in their path is briefly deformed. The effect is incredibly small. A gravitational wave passing through Earth might change distances by less than the width of a proton. But we have learned to detect them. In 2015, scientists measured gravitational waves for the first time. The signal came from two black holes merging over 1 billion light-years away. We now have a new sense, a way to feel the vibrations of the cosmos, a way to hear the silent collisions in the dark. Gravitational waves are the sound of space-time itself. Neutron stars are the densest objects we can observe directly. When a massive star collapses but not quite enough to form a black hole, it becomes a neutron star. An object about 20 kilometers across, but containing more mass than the Sun. The matter inside is compressed so tightly that atoms are crushed together. Protons and electrons merge into neutrons. The entire star becomes a single atomic nucleus. A teaspoon of neutron star material would weigh billions of tons on Earth. More than entire mountains. Some neutron stars spin hundreds of times per second, sending beams of radiation sweeping across the sky like cosmic lighthouses. We call these pulsars. Others have magnetic fields trillions of times stronger than Earth's. We call these magnetars. Neutron stars are extreme. They exist at the boundary of what matter can withstand. Any denser, and they would collapse into black holes. They are the universe's densest survivors. The elements in your body were forged in stars. Hydrogen and helium were created in the first minutes after the beginning. But everything else, the carbon, the oxygen, the iron, was created later. Stars are nuclear furnaces. In their cores, lighter elements are fused into heavier ones. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen. And so on up the periodic table. When massive stars die, they explode as supernovae, scattering these newly forged elements across space. Those elements mix into clouds of gas. Those clouds collapse into new stars, new planets, new life. The calcium in your bones was created inside a star. The iron in your blood was forged in a supernova. The oxygen you breathe was born in stellar cores billions of years ago. You are made of stardust. Literally, physically, chemically. The universe spent billions of years creating the atoms that would become you. And one day, those atoms will return to the cosmos to be used again. Nucleosynthesis is the cosmic process of element creation. In the cores of stars, nuclear fusion combines lighter elements into heavier ones. This process releases the energy that makes stars shine. The fusion chain begins with hydrogen. 4 hydrogen nuclei combine to form one helium nucleus, releasing tremendous energy. This powers most stars for billions of years. As stars age and their cores grow hotter, they fuse heavier elements. Helium becomes carbon, carbon becomes oxygen, oxygen becomes neon, then magnesium, then silicon. The process continues until iron. Iron cannot release energy through fusion. When a massive star's core becomes iron, the furnace stops. The star collapses. Explosion follows. Elements heavier than iron are created during supernovae themselves or in neutron star collisions. Gold, platinum, uranium, all forged in cosmic catastrophes. The periodic table is a record of cosmic history. Each element tells a story of stellar lives and deaths. The heaviest elements require the most violent events. Gold is not made in ordinary stars. Neither is platinum nor uranium. These elements form when neutrons are captured by atomic nuclei faster than they can decay. This requires extreme conditions, the kind found only in supernovae or when neutron stars collide. When two neutron stars merge, they create a kilonova. In seconds, enormous quantities of heavy elements are synthesized and scattered into space. The gold in your jewelry, the lead in old pipes, the uranium in nuclear reactors, all were created in the deaths of stars or the collisions of stellar corpses. The universe builds its treasures through destruction. Stellar winds carry material into space. Not all mass loss from stars happens through explosions. Many stars continuously blow material into space through stellar winds. Our Sun loses about 1 million tons of mass every second through its solar wind. This seems like a lot, but it is a tiny fraction of the Sun's total mass. More massive stars have much stronger winds. They can lose significant fractions of their mass before they die. These winds enrich the interstellar medium with elements forged in stellar cores. They contribute to the chemical evolution of galaxies. Stars share their substance continuously, not just in death, but throughout their lives. Binary stars can exchange mass. When two stars orbit close together, the larger one can pull material from its companion. This mass transfer can dramatically alter both stars. The star losing mass may shrink. The star gaining mass may grow, spin faster, or even explode. Some of the most spectacular events in the universe, like certain types of supernovae and X-ray binaries, result from mass exchange between stellar partners. Stars influence each other. Gravity connects them across the void. The universe is relational. Nothing exists entirely alone. Variable stars change brightness over time. Not all stars shine steadily. Many vary in brightness over hours, days, or years. Some pulsate, swelling and shrinking rhythmically. Others rotate, showing brighter and dimmer sides. Some are eclipsed by companion stars passing in front. Cepheid variables are particularly important. Their pulsation periods are related to their intrinsic brightness. By measuring the period, astronomers can calculate the true luminosity and thus the distance. Cepheids were used to prove that other galaxies exist beyond the Milky Way. They remain essential tools for measuring cosmic distances. The universe provides natural calibration standards. We use them to map the cosmos. Some stars explode with the brightness of entire galaxies. A supernova is one of the most violent events in the universe. When a massive star exhausts its fuel, its core collapses in seconds. The outer layers rebound in a catastrophic explosion. For a brief time, a single dying star can outshine all the other stars in its galaxy combined. Hundreds of billions of suns, momentarily surpassed by one. The explosion sends a shockwave racing outward. It creates new elements through rapid nuclear reactions. It scatters heavy atoms across light years. Supernovae are essential. Without them, the elements needed for rocky planets and living things would remain locked inside stars forever. Every supernova is a gift, a final act of cosmic generosity from a dying star. The light from some stars takes so long to reach us that those stars may already be dead. When you look at a star in the night sky, you are seeing it as it was when its light began the journey. For nearby stars, this is only years or decades. But for distant stars, it can be thousands or millions of years. Some of the stars you see may no longer exist. They may have exploded, collapsed, or faded long ago. But their light still travels, a message from the past still arriving at your eyes. This is true of everything we observe in space. The moon as it was just over a second ago. The sun as it was 8 minutes ago. Distant galaxies as they were billions of years before Earth formed. We can never see the present. Only the past, arriving continuously from every direction. The universe appears to be the same in every direction. When we look out into space, we find galaxies everywhere. Not clustered in one direction and empty in another, but spread more or less evenly across the entire sky. This uniformity is called isotropy, and it tells us something profound about the early universe. If different regions had been significantly different, we would see that difference today. Instead, the cosmic microwave background is nearly identical in all directions. Galaxies are distributed similarly everywhere we look. This suggests that the early universe was remarkably smooth. Any variations were tiny, and the same physical processes operated everywhere. The universe is not chaotic. It is ordered, consistent, governed by the same laws from edge to edge. The universe also appears the same at every location. This is called homogeneity. On the largest scales, no place in the universe is special. There is no center, no edge, no preferred position. An observer in a distant galaxy would see the same thing we see. Galaxies in every direction. An expanding cosmos. Ancient light filling the sky. This principle, that the universe looks the same from everywhere, is fundamental to modern cosmology. It allows us to make predictions about regions we will never visit. You are not at the center of the universe, but neither is anywhere else. Every point has an equal claim to centrality, or none does. Galaxies cluster together along vast cosmic filaments. When we map the positions of millions of galaxies, a pattern emerges. Galaxies are not scattered randomly. They gather along long thread-like structures called filaments. These filaments stretch for hundreds of millions of light years. They connect denser regions called nodes where galaxies cluster tightly. Between the filaments lie enormous voids, regions of space nearly empty of galaxies. Some voids span hundreds of millions of light years. This pattern is called the cosmic web. It is the largest structure in the universe. The filaments trace the distribution of dark matter. Gravity pulled matter together along these invisible threads, and galaxies formed where matter collected. The cosmic web is like a skeleton, an invisible framework upon which the visible universe hangs. The largest known structures are galaxy superclusters. Galaxies gather into groups, groups gather into clusters, and clusters gather into superclusters. Our own Milky Way belongs to the local group, which belongs to the Virgo supercluster, which is part of an even larger structure called Laniakea. Laniakea spans over 500 million light-years. It contains over 100,000 galaxies, all connected by gravity, all flowing slowly toward a common gravitational attractor. These superclusters are the largest gravitationally bound structures in the universe. Beyond them, cosmic expansion takes over, and structures drift apart. We live in a small corner of an immense gathering. A single galaxy in a web of galaxies stretching beyond imagination. The universe contains voids hundreds of millions of light-years across. Between the filaments and clusters lie the cosmic voids. Enormous regions almost entirely empty of galaxies. Some voids are so large that light would take hundreds of millions of years to cross them. And yet they contain almost nothing. Just scattered galaxies floating in the emptiness. These voids are not truly empty. They contain gas, dark matter, and the faint glow of the cosmic microwave background. But compared to the dense filaments, they are desolate. The universe is not uniformly filled. It has structure. Dense regions and empty regions. Light and darkness woven together. If you could travel through a void, you would see fewer and fewer galaxies until you were surrounded by near total emptiness. The nearest galaxy might be tens of millions of light-years away. The universe has room for emptiness as vast as its fullness. There may be other universes beyond our own. This is speculation, not established science. But some theories of physics suggest that our universe may be one of many. Perhaps the conditions that created our cosmos also created others. Perhaps our universe bubbled off from a larger reality. Perhaps different regions of space underwent different initial conditions and became separate universes with different laws of physics. These ideas are collectively called the multiverse. They remain unproven, perhaps unprovable. We cannot observe beyond our own cosmic horizon. But the possibility lingers. Our universe, vast as it is, may be just one room in an infinite mansion. If true, the cosmos is even stranger than we imagined. The anthropic principle asks why the universe is suitable for life. The laws of physics seem finely tuned. Small changes to fundamental constants would make stars impossible, chemistry non-existent, or the universe itself unstable. Why do the constants have the values they do? One answer is the anthropic principle. We observe a universe suitable for life, because only such universes can be observed. If the multiverse is real, most universes may be lifeless. We exist in one where life is possible simply because we could not exist anywhere else. This reasoning is controversial. It explains little and predicts less. But it highlights how special our universe appears. Whether by design, chance, or selection, we inhabit a cosmos that allows us to wonder why. Some physicists seek a theory of everything. The four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, govern all physical phenomena. Physicists have successfully unified three of these forces at high energies. But gravity remains separate, described by general relativity rather than quantum mechanics. A theory of everything would unify all four forces into a single framework. It would explain why the constants have their values. It would reveal the deep structure of reality. String theory and loop quantum gravity are candidates. Neither has been verified experimentally. The search continues. The universe may have a simple underlying structure. We are still looking for it. The universe may be a closed system. Energy cannot be created or destroyed within the universe. It can only change form. The total energy of the universe may be zero. The positive energy of matter and radiation, balanced by the negative energy of gravity. If so, the universe could have emerged from nothing without violating conservation laws. The Big Bang may have been a quantum fluctuation that balanced itself. This idea is speculative, but it suggests that the universe did not require external input. It may be self-contained, self-created, complete. The cosmos may have bootstrapped itself into existence. Information may be fundamental to reality. Some physicists argue that information is as fundamental as matter and energy. The universe can be described as a vast network of information processing. Every particle carries information about its state. Every interaction is a computation. The laws of physics are rules for how information evolves. This view is not yet mainstream, but it offers a new perspective on reality. Perhaps the universe is not just made of stuff. Perhaps it is made of relationships, patterns, knowledge. The cosmos may be more like a thought than a thing. The speed of light is a universal speed limit. Nothing can travel through space faster than light. This is not a technological limitation. It is built into the structure of space-time. As an object with mass approaches the speed of light, it requires more and more energy to accelerate further. Reaching light speed would require infinite energy. Only massless particles like photons can travel at light speed. Everything else is slower. This speed limit ensures causality. Effects cannot precede causes. The universe has a maximum rate at which information can travel. Light speed is not just fast. It is the fastest possible. The early universe underwent a period of unimaginably rapid expansion called inflation. In the first tiny fraction of a second after the beginning, space expanded faster than light. Regions that were once in contact were flung so far apart that they could never communicate again. This process, called cosmic inflation, explains several puzzles about the universe. Why is it so flat? Why is the cosmic microwave background so uniform? Why do distant regions share similar properties? Inflation smoothed everything out. It stretched tiny quantum fluctuations into the seeds of cosmic structure. It set the stage for everything that followed. Inflation ended quickly, in less than a billionth of a second. But in that brief moment, the universe grew by an unimaginable factor. The cosmos we see today is the aftermath of that explosive birth. Quantum fluctuations in the early universe became the seeds of galaxies. At the smallest scales, reality is fuzzy. Particles flicker in and out of existence. Energy fluctuates randomly. Nothing is perfectly still. During inflation, these tiny quantum fluctuations were stretched to cosmic scales. Regions slightly denser than average attracted more matter. Regions slightly less dense became voids. Over billions of years, gravity amplified these differences. Dense regions collapsed into galaxies. Voids grew emptier. The structure of the universe, every galaxy, every cluster, every filament, traces back to random quantum jitters in the first instant of time. Chance became structure. Randomness became order. The universe built itself from noise. The universe will continue expanding forever. Current observations suggest that the expansion of the universe will never stop. There is not enough matter to pull everything back together. Dark energy will continue accelerating the expansion. Galaxies will drift farther apart. The night sky will grow darker. Eventually, even nearby galaxies will recede beyond the cosmic horizon. In the far future, observers in any galaxy will see only their own stars. The rest of the universe will have faded from view. This fate is called the Big Freeze, or heat death. A slow, quiet ending stretching over trillions of years. Not a bang, but a whisper. Not fire, but ice. The Big Rip is an alternative cosmic fate. If dark energy strengthens over time, the expansion of the universe could accelerate without limit. Eventually, the expansion would overcome gravity on smaller and smaller scales. First, galaxy clusters would separate. Then galaxies themselves would be torn apart. Stars would be ripped from their orbits. Planets would fly away from their suns. In the final moments, atoms themselves would be torn apart. The fabric of space would shred into disconnected fragments. This scenario is called the Big Rip. It depends on the nature of dark energy, which we do not fully understand. Current evidence suggests dark energy is constant, making the Big Rip unlikely. But we cannot be certain. The future is not yet written. The Big Crunch is another possibility, now considered unlikely. Before dark energy was discovered, cosmologists considered another fate. Perhaps the universe would eventually stop expanding and begin to contract. As the cosmos collapsed, galaxies would merge. The temperature would rise. Eventually, everything would compress back into a singularity, a reverse of the Big Bang. This scenario is called the Big Crunch. It is poetic. A universe that begins and ends in the same way. but the discovery of accelerating expansion made the Big Crunch unlikely. The universe appears destined to expand forever. Still, the Big Crunch reminds us that our understanding could be wrong. The cosmos may yet surprise us. The universe may experience a phase transition in the distant future. The vacuum of space may not be in its most stable state. There may be a lower energy configuration that the universe has not yet reached. If the vacuum suddenly transitioned to this lower state, the effects would be catastrophic. A bubble of true vacuum would expand at the speed of light, destroying everything in its path. Atoms would fall apart. Chemistry would change. The universe as we know it would end. This scenario is highly speculative. The vacuum appears stable over cosmic timescales. But absolute stability cannot be proven. The universe may be resting on a precarious ledge, stable enough for now, but not forever. Stars will stop forming in the distant future. Star formation requires cold gas. Clouds of hydrogen that can collapse under gravity. But the universe is running out of this raw material. Gas is being consumed by existing stars. It is being heated and dispersed by supernovae. And it is being pushed apart by cosmic expansion. In approximately 100 trillion years, star formation will cease. The last stars will be born. After that, no more. The universe will contain only the stars that already exist, and those will slowly die, one by one, over unimaginable spans of time. The cosmos will grow dark, but even then, it will not be truly empty. Red dwarf stars will be the last to shine. The smallest stars burn their fuel most slowly. Red dwarfs, dim and cool, can live for trillions of years. When larger stars have all died, red dwarfs will continue to glow faintly in the darkness. The last lights in a cooling cosmos. Some red dwarfs born today will still be shining when the universe is 100 times its current age. Eventually, even they will exhaust their fuel. Their light will fade. The cosmos will grow darker still. But for an almost unimaginable span of time, red dwarfs will carry on. The patient survivors of a dying universe. The longest-lived stars will burn for trillions of years. Not all stars die quickly. The smallest red dwarfs, barely massive enough to sustain fusion, burn their fuel with extreme efficiency. These dim, cool stars may live for trillions of years, far longer than the current age of the universe. When larger stars have all died, red dwarfs will continue to glow faintly in the darkness. The last lights in a cooling cosmos. Eventually, even they will exhaust their fuel. Their cores will cool. Their light will fade. And they will become cold, dark remnants drifting through endless night. But that ending is so far in the future that our current universe is still in its infancy, by comparison. White dwarfs will cool into black dwarfs over quadrillions of years. When a star like our Sun dies, it leaves behind a white dwarf, a dense remnant slowly radiating away its remaining heat. White dwarfs cool extremely slowly. Their heat capacity is immense. It will take quadrillions of years for them to cool completely. When they finally stop glowing, they will become black dwarfs. Dark, cold spheres of carbon and oxygen drifting through space. No black dwarfs exist yet. The universe is too young. But one day, the cosmos will be filled with them. Silent witnesses to an ancient past. Graves of stars long forgotten. Black holes will eventually evaporate through Hawking radiation. Even black holes do not last forever. According to quantum physics, they slowly leak energy through a process called Hawking radiation. Particles flicker into existence near the event horizon. Sometimes one particle escapes while the other falls in. Over time, this drains energy from the black hole. The process is incredibly slow. A black hole with the mass of the Sun would take longer than 10 to the power of 67 years to evaporate completely. But eventually, all black holes will vanish. Even the supermassive black holes at the centers of galaxies. Even the largest ever formed. In the end, the universe will contain only particles, radiation, and empty space. Everything else will have decayed away. The final state of the cosmos is silence. The universe may experience a heat death. Entropy is a measure of disorder. And according to the laws of thermodynamics, entropy always increases. Over time, energy spreads out. Hot things cool, cold things stay cold. Eventually, everything reaches the same temperature. In this final state, no work can be done, no processes can occur. The universe reaches maximum entropy, perfect equilibrium, total stillness. This is heat death, not a violent ending, not a collapse, just a slow fading into uniformity. The stars will be gone, the galaxies dissolved, even the atoms may have decayed. What remains is a sea of particles at the same temperature throughout. No change. No time in any meaningful sense. Just being. Time may have no meaning in the distant future. Time is measured by change. The ticking of a clock. The beating of a heart. The rotation of planets. In a universe at heat death, there is no change. Nothing happens. Nothing moves. Nothing evolves. Does time still pass in such a universe? Philosophers and physicists disagree. Perhaps time continues, stretching infinitely forward, with nothing happening within it. Or perhaps time itself loses meaning when there is nothing left to measure it. The future of the universe is strange, stranger than we can truly imagine. The universe may be a simulation. This is a philosophical hypothesis, not established science. But some thinkers have suggested that our entire reality could be a computer simulation run by some vastly advanced intelligence. If civilizations can create convincing simulations of reality, and if they would want to, then there might be far more simulated universes than real ones. In that case, we might be more likely to exist inside a simulation than outside one. This idea cannot be tested. There is no way to peek behind the curtain. But it raises unsettling questions about the nature of existence. What does it mean to be real? Is there a difference between reality and perfect simulation? The universe does not easily answer such questions. Consciousness may be more widespread than we assume. We know that consciousness exists because we experience it, but we do not understand how or why. Some scientists believe consciousness emerges from sufficiently complex information processing. If so, it might arise in any sufficiently advanced system, whether biological or artificial. Others believe consciousness is more fundamental, perhaps a basic property of the universe itself, perhaps woven into the fabric of reality alongside space, time, matter, and energy. If consciousness is widespread, the universe may be more aware than we imagine. Minds scattered across galaxies. Awareness flickering in countless forms. We simply do not know. The mystery of consciousness remains one of the deepest puzzles of all. The fine structure constant determines the strength of electromagnetic interactions. There are certain numbers in physics that seem finely tuned. If they were slightly different, the universe as we know it could not exist. The fine structure constant, approximately 1/137, governs the strength of interactions between light and matter. If this constant were slightly larger, stars might burn too quickly. If it were smaller, chemistry might not work as it does. Why does this constant have the value it does? We do not know. Perhaps it is random. Perhaps it arises from deeper physics we have not yet discovered. The universe seems calibrated. Whether by chance, necessity, or something else, we cannot say. The cosmological constant determines the rate of cosmic expansion. Dark energy is characterized by a value called the cosmological constant. This tiny number determines how quickly the universe expands. Remarkably, the cosmological constant is extremely small. If it were much larger, the universe would have expanded too fast for galaxies to form. Why is it so small? Why is it not zero? These questions are among the greatest mysteries in physics. Some theorists suggest that there may be many universes with different values, and we exist in one where the value happens to allow galaxies and stars and life. Others seek a deeper explanation. None has yet been found. The universe keeps its secrets well. The observable universe is about 93 billion light-years across. This number seems impossible. If the universe is only 13.8 billion years old, how can we see things 93 billion light-years away? The answer is expansion. While light has been traveling toward us for billions of years, the space it crossed has been stretching. Objects that were once closer are now much farther away. The light began its journey from a relatively nearby location, but that location has since been carried away by cosmic expansion. The observable universe is a sphere with us at the center. Not because we are special, but because we can only see light that has had time to reach us. Beyond that sphere lies more universe. Perhaps infinitely more, but we cannot see it. Light is both a wave and a particle. This is one of the strangest discoveries of the 20th century. Light behaves sometimes as a wave, spreading out and interfering with itself, and sometimes as a particle, arriving in discrete packets called photons. Neither description alone is complete. Light is something else. Something that our everyday intuitions struggle to grasp. This wave-particle duality is not unique to light. All particles exhibit it. Electrons, protons, even atoms. At the quantum level, reality is not quite what we expect. Things do not have definite positions until they are measured. Outcomes are probabilistic, not certain. The universe is built on uncertainty. Yet from uncertainty, extraordinary order emerges. The Heisenberg uncertainty principle limits what we can know. There is a fundamental limit to how precisely we can measure certain pairs of properties. The more precisely we know a particle's position, the less precisely we can know its momentum. And vice versa. This is not a limitation of our instruments. It is built into the fabric of reality. The universe itself does not have definite values for both properties simultaneously. This principle underlies all of quantum mechanics. It explains why particles behave probabilistically. It sets boundaries on knowledge itself. The universe permits mystery. Some things cannot be known with perfect precision. Not because we are ignorant, but because the cosmos is fundamentally fuzzy. Entangled particles remain connected across any distance. When two particles become entangled, their properties become linked. Measuring one instantly affects the other, no matter how far apart they are. This is not communication. No information travels between them faster than light. But the correlation is real. The outcomes are connected. Einstein called this spooky action at a distance. He found it troubling. But experiment after experiment has confirmed it. Entanglement reveals that reality is non-local. The universe is more interconnected than we intuitively expect. Particles separated by billions of light-years can still be correlated. The cosmos is woven together in ways we are only beginning to understand. The universe may contain regions with different physical laws. In some theories, the constants of physics are not truly constant. They may vary from place to place, established randomly in different regions during cosmic inflation. If so, our observable universe has one set of laws, but other regions may have different values. Different chemistry, different forces, perhaps no possibility of life. We can never visit these regions. They are beyond our cosmic horizon. But their existence, if real, would make our universe just one of many possible configurations. The laws of physics may not be universal after all. They may be local, contingent, one possibility among countless others. Antimatter is identical to matter, but with opposite charge. For every particle, there exists an antiparticle. An electron has a positron. A proton has an antiproton. They are identical in mass, but opposite in charge. When matter and antimatter meet, they annihilate each other, converting their mass entirely into energy. In the early universe, matter and antimatter were created in almost equal amounts. Almost. A tiny asymmetry, about 1 part in a billion, led to more matter than antimatter. That slight excess is why we exist. Everything we see, every star, every planet, every person, is made from the leftovers of that ancient imbalance. Where did the asymmetry come from? We do not know for certain. It remains one of the great puzzles of cosmology. Neutrinos pass through ordinary matter almost without interaction. Trillions of neutrinos pass through your body every second. They come from the Sun, from distant supernovae, from the early universe itself. Yet they almost never interact with the atoms you are made of. A neutrino could pass through a light year of solid lead, with a good chance of emerging unscathed. Detecting them requires enormous underground detectors, shielded from other particles, waiting for the rare collision. Neutrinos are ghostly messengers. They carry information from places we cannot otherwise see. The cores of stars, the hearts of explosions, the first seconds after the beginning. The universe is filled with invisible travelers. We are bathed in their silent passage, constantly. The cosmic microwave background has a temperature of about 2.7 Kelvin. This ancient light fills the entire universe. It is the cooled remnant of the hot plasma that filled space 380,000 years after the beginning. Its temperature is now just a few degrees above absolute zero. Still warm enough to detect, still carrying information about the early cosmos. This background radiation is remarkably uniform, but not perfectly so. Tiny variations, differing by only a few parts in 100,000, reveal the seeds of all future structure. Maps of the cosmic microwave background are maps of the infant universe. The patterns we see became the galaxies we observe today. We carry this ancient light with us everywhere. It surrounds us constantly. The faint glow of the universe's childhood. Some stars are older than 13 billion years. The oldest stars in the universe formed shortly after the first galaxies began to assemble. Some of these ancient stars still exist today. They are found in the halos of galaxies, in globular clusters, in the outskirts of cosmic structures. They contain very few heavy elements, because heavy elements had not yet been created when they formed. These stars are fossils. They preserve the chemical signatures of the early universe. By studying them, we learn about conditions that existed billions of years before Earth formed. Some stars have been burning quietly for over 13 billion years. Nearly as old as the universe itself. They are the universe's oldest survivors. Still glowing, still waiting to be observed. The first stars may have been giants. When the universe was young, the clouds of gas contained only hydrogen and helium. These clouds collapsed to form the first stars. Without heavier elements, these primordial stars may have been enormous, hundreds of times more massive than our Sun, burning hot and bright and dying quickly. They lived for only a few million years before exploding as supernovae or collapsing into black holes. But in their brief lives, they created the first heavy elements. These first stars have never been directly observed. They died long ago. But their fingerprints remain in the chemistry of the universe. They were the ancestors of all the stars we see today, the pioneers of light in a dark cosmos. Galaxies grow by merging with other galaxies. The Milky Way has consumed smaller galaxies throughout its history, and it will merge with the Andromeda Galaxy in a few billion years. Galaxy mergers are violent events on cosmic scales. Stars are flung into new orbits. Gas is compressed, triggering bursts of star formation. Black holes may collide and merge. Yet the stars themselves rarely collide. Galaxies are mostly empty space. Two galaxies can pass through each other, with their stars missing by light years. The universe builds larger structures through these slow collisions. Small galaxies become medium galaxies. Medium galaxies become giant ellipticals. The cosmos is a construction site. Galaxies are still being assembled. The universe was once too hot for atoms to exist. In the first hundreds of thousands of years, the universe was a sea of plasma. Electrons were too energetic to bind to nuclei. Atoms could not form. Light could not travel freely because it was constantly scattered by free electrons. The universe was opaque. Only when temperatures dropped below about 3000 Kelvin did electrons slow enough to be captured by nuclei. Hydrogen atoms formed. Then helium. This moment, called recombination, released the cosmic microwave background. The universe became transparent. Light could finally travel across the cosmos. The transition from chaos to clarity happened once. We still see its echo everywhere we look. There are more stars in the universe than grains of sand on Earth. Estimates suggest the observable universe contains about 200 billion trillion stars. That is a 2 followed by 23 zeros. Earth's beaches and deserts contain perhaps 7 sextillion grains of sand. That is a 7 followed by 21 zeros. Stars outnumber sand by a factor of about 30. This is a humbling comparison. Looking at a sandy beach, you see more grains than you could ever count. Yet the stars exceed even that. The universe is filled with lights beyond counting. Each one a sun. Many with their own worlds. The sun is an ordinary star. Our sun is not special. It is a yellow dwarf, average in size, average in brightness, average in temperature. There are billions of similar stars in the Milky Way alone, and billions of galaxies beyond. This ordinariness is comforting. It means that the conditions that allowed life on Earth might exist elsewhere. Stars like ours are common. Our sun will burn for another 5 billion years before expanding into a red giant and shedding its outer layers. It is a gentle, stable star, neither too bright nor too dim, just right for the kind of life we know. But it is not unique. It is one of countless similar suns scattered throughout the cosmos. The nearest star is over 4 light-years away. Proxima Centauri, the closest star to our Sun, is about 4.2 light-years distant. That means light from Proxima takes over 4 years to reach us. If you could travel at the speed of light, the journey would take more than 4 years. At the speed of our fastest spacecraft, the journey would take tens of thousands of years. The distances between stars are immense. Even our nearest neighbors are almost unimaginably far. The stars may seem close together in the night sky, but they are separated by voids so vast that crossing them seems nearly impossible. Space is mostly empty. Stars are lonely islands scattered across an ocean of darkness. The night sky contains only a tiny fraction of the galaxy's stars. When you look up on a clear night, you might see a few thousand stars. Perhaps 6,000 if your sky is perfectly dark and your eyes are sharp. But the Milky Way contains hundreds of billions of stars. Most are too faint, too distant, or hidden behind dust clouds. The stars we see are mostly nearby, within a few hundred light-years, barely scratching the surface of the galaxy. Beyond what we see lies an ocean of stars, stretching across 100,000 light-years, hidden by distance and dust and the limits of human vision. The night sky is a window, a small one. Through it, we glimpse only a fraction of the cosmos that surrounds us. The universe is full of radiation we cannot see. Visible light is only a narrow slice of the electromagnetic spectrum. Beyond it lies infrared, microwave, radio. Below it lies ultraviolet, X-ray, gamma ray. The universe emits radiation across this entire spectrum. Galaxies glow in infrared. Neutron stars pulse in X-rays. Black hole jets blast gamma rays. Most of this radiation is invisible to human eyes. We need instruments to detect it. When we observe the universe in different wavelengths, we see different things. Hidden structures revealed. Invisible processes illuminated. The visible universe is only part of the story. Most of the cosmic light is beyond our sight. The universe is expanding faster than expected. When astronomers measure the expansion rate of the universe using nearby objects, they get one number. When they measure it using the cosmic microwave background, they get a different number. These measurements should agree, but they don't. The difference is called the Hubble tension. Either our measurements are wrong, or our understanding of the universe is incomplete. Perhaps some unknown physics is at work. This discrepancy is one of the great puzzles of modern cosmology. It suggests that the cosmos may hold surprises we have not yet imagined. The universe does not always behave as expected. It keeps revealing new mysteries. The cosmic noon was the peak of star formation. About 10 billion years ago, the universe reached its maximum rate of star formation. Galaxies were building stars at an incredible pace. This era is called cosmic noon. More stars were born during this period than at any other time in cosmic history. Since then, star formation has declined. Gas is running out. The universe is settling into a slower phase. We live in the cosmic afternoon. The peak is behind us, but there is still light left to burn. The sun travels around the galaxy at incredible speed. Our solar system does not sit still. It orbits the center of the Milky Way at approximately 800,000 kilometers per hour. At this tremendous velocity, the sun and all its planets race through space like passengers on a cosmic carousel. Yet even at this speed, it takes about 225 million years to complete a single orbit. This period is sometimes called a galactic year. In all its existence, our Sun has made this journey only about 20 times. The last time Earth was in this position, dinosaurs roamed the land. The next time, our world will be unrecognizable. We are always moving, even when we feel still. cosmic rays constantly bombard Earth from deep space. High-energy particles called cosmic rays stream through the universe at nearly the speed of light. They come from supernovae, black holes, and other violent cosmic events. Most are deflected by Earth's magnetic field or absorbed by the atmosphere. But some reach the surface. A few cosmic ray particles pass through your body every second. They are mostly harmless in small numbers. These particles carry information from distant explosions. They are messengers from across the galaxy. The universe reaches out and touches us constantly. Even in the quiet of night, the universe has no center. It seems intuitive that the universe should have a center, a point from which everything expands. But it does not. The Big Bang did not happen at a specific location in space. It happened everywhere simultaneously. Every point in the universe was once compressed into the initial singularity. As space expanded, every point moved away from every other point. There is no privileged center, no special location. An observer anywhere in the universe would see the same thing we see. Galaxies receding in all directions. Expansion happening everywhere. We are not at the center of the universe, but neither is anywhere else. Some galaxies spin in the wrong direction. When astronomers survey galaxies, they find that most rotate in predictable ways based on how they formed. But a small percentage rotate backward. These retrograde galaxies may have formed through unusual mergers. Or perhaps their angular momentum was reversed by gravitational interactions. Understanding why some galaxies break the pattern helps us understand how cosmic structures form. The universe has room for exceptions. Not everything follows the expected rules. Quasars are the brightest objects in the universe. At the centers of some distant galaxies lie supermassive black holes, actively consuming matter. As gas spirals inward, it heats to extreme temperatures and radiates tremendous energy. These active galactic nuclei are called quasars. They can outshine their entire host galaxy by factors of thousands. Some quasars are so bright they can be seen across billions of light years. They appeared when the universe was young. Most quasars have since faded as their black holes consumed the available gas. But their light continues to arrive, carrying information from the ancient cosmos. Quasars are beacons from the past. Signposts marking the locations of the universe's most massive objects. The universe may have undergone phase transitions. Just as water can freeze or boil, the universe may have changed its fundamental nature at key moments. During the first fractions of a second, as temperatures dropped, the forces of nature may have separated into distinct interactions. Particles may have gained mass. New physics may have emerged. These cosmic phase transitions are theorized but not directly observed. They would have released tremendous energy, potentially generating cosmic structures we still see today. The universe is not static. It has evolved through distinct eras, each with different properties. We live in a late phase. The universe has already changed fundamentally several times since the beginning. pulsars are cosmic clocks of extraordinary precision. Some neutron stars emit beams of radiation that sweep across space like lighthouse beams. When these beams cross Earth's line of sight, we detect regular pulses. These pulsars are remarkably stable. Some pulse hundreds of times per second, with variations smaller than atomic clocks. Astronomers use pulsars to test theories of gravity, detect gravitational waves, and map the interstellar medium. The universe has built natural timekeepers, objects that tick with precision we can barely match. Somewhere, a pulsar that began spinning before Earth formed is still counting time. Fast radio bursts remain largely unexplained. In recent years, astronomers have detected brief, intense bursts of radio waves from deep space. These fast radio bursts last only milliseconds, but release as much energy as the Sun emits in days. Most come from distant galaxies. Some repeat, others flash once and never again. We do not fully understand what causes them. Theories range from magnetar flares to exotic physics. The universe still surprises us. New phenomena are discovered regularly. Each discovery reminds us how much remains unknown. The cosmos is not finished revealing its secrets. Binary stars are more common than single stars. Our Sun is alone. But this is unusual. Most stars form in pairs or multiples. Binary stars orbit each other, sometimes close enough to exchange material. Some spiral together and merge. Others maintain stable dances for billions of years. Studying binary stars helps us measure stellar masses and understand stellar evolution. The universe prefers company. Stars tend to form together, bound by gravity, circling each other through the ages. Solitary stars like our Sun may be the exceptions rather than the rule. Some galaxies are being torn apart by larger neighbors. When a small galaxy passes too close to a larger one, tidal forces can stretch and distort it. Stars are pulled into long streams. Gas is stripped away. Eventually, the smaller galaxy may be absorbed completely. We see evidence of such galactic cannibalism throughout the universe. The Milky Way itself has consumed smaller galaxies and will eventually merge with Andromeda. Galaxies are not permanent. They evolve, interact, and sometimes devour each other. The universe is always under construction. The interstellar medium is not empty. Between the stars lies a thin soup of gas and dust called the interstellar medium. It is incredibly sparse. Only about 1 atom per cubic centimeter on average. Yet across the vast distances between stars, this material adds up. It can dim starlight, scatter radiation, and provide raw material for new star formation. The interstellar medium is not uniform. Dense clouds called molecular clouds are the birthplaces of stars. Thinner regions allow light to pass freely. Space is not truly empty. It is filled with the remnants of ancient stars and the seeds of future ones. Stars end their lives in different ways, depending on their mass. Low-mass stars like our Sun will swell into red giants. shed their outer layers, and leave behind white dwarfs. More massive stars will explode as supernovae, leaving behind neutron stars or black holes. The most massive stars may collapse directly into black holes, without any explosion at all. Each ending scatters elements into space. Each ending changes the chemistry of the universe. Stars give their gifts in death as in life. The Andromeda Galaxy is approaching us. Unlike most galaxies which are receding due to cosmic expansion, Andromeda is moving toward the Milky Way. In about 4 billion years, the two galaxies will collide. Not destructively, stars will mostly pass by each other, but transformatively. The merger will take hundreds of millions of years. Gas clouds will compress, triggering new star formation. The combined galaxy will eventually settle into a new shape. We will not be here to see it, but it is comforting to know that our galaxy will not end alone. It will join with another in a slow cosmic embrace. The observable universe is not the whole universe. We can only see light that has had time to reach us. The observable universe is a sphere centered on Earth, limited by the age of the cosmos and the speed of light. Beyond that sphere lies more universe, perhaps much more, perhaps infinitely more. We cannot see it, we cannot measure it, we cannot know how large the whole truly is. The observable universe contains about 2 trillion galaxies. The actual universe may contain far more. We see only a fraction of what exists. Cosmic inflation may have created multiple universes. If cosmic inflation happened once, it may have happened many times. Different regions of space may have inflated into separate bubbles, each becoming its own universe. These bubble universes would be forever disconnected from ours. No light, no signal, no information could travel between them. If this is true, the multiverse is real. Our universe is one of countless others, each with potentially different properties. This idea cannot be tested with current technology, but it arises naturally from some theories of inflation. The cosmos may be vaster than even our most expansive imaginings. Gamma-ray bursts are the most energetic explosions since the Big Bang. When certain massive stars collapse or when neutron stars merge, they can release brief but incredibly powerful bursts of gamma rays. These gamma ray bursts can release more energy in seconds than the Sun will emit in its entire lifetime. If one occurred nearby and pointed at Earth, it could strip away our atmosphere and sterilize the planet. Fortunately, such events are rare and usually distant. The gamma-ray bursts we detect come from billions of light-years away. The universe contains forces of tremendous destructive power. We are fortunate to observe them from a safe distance. Dark matter halos surround galaxies. The visible part of a galaxy, the stars, gas, and dust, is embedded in a much larger halo of dark matter. This invisible halo extends far beyond the visible edge of the galaxy. It contains most of the galaxy's mass. Dark matter halos shape how galaxies rotate, how they cluster together, and how light bends around them. We cannot see these halos directly, but we can infer their presence from the motions of stars and the bending of light. Every galaxy we see floats within an invisible cocoon of dark matter. The universe is getting lonelier. As cosmic expansion accelerates, galaxies are carried farther apart. Eventually, the light from distant galaxies will take so long to reach us that they will fade from view. In the far future, observers in our local group will see only nearby galaxies. The rest of the universe will have receded beyond their cosmic horizon. The night sky will grow darker. The universe will seem smaller. This loneliness is billions of years away, but it is inevitable unless physics changes. The cosmos is slowly separating into isolated islands of light. Gravitational lensing can reveal hidden objects. When light passes near a massive object, gravity bends its path. This can magnify and distort the images of objects behind it. Astronomers use gravitational lensing to study distant galaxies, detect dark matter, and find exoplanets. Sometimes the lensing creates multiple images of the same object. Sometimes it forms arcs or rings. Light becomes a tool for seeing what would otherwise be invisible. The universe bends itself into a natural telescope. Some black holes spin at nearly the speed of light. Black holes can rotate. As they consume matter, they often gain angular momentum. Some black holes spin so fast that their equators approach the speed of light. Spinning black holes drag space-time around them, creating regions where nothing can remain stationary. These spinning monsters are among the most extreme objects in the universe. Their rotation affects everything nearby. Even darkness can have motion. Stellar nurseries glow with the light of newborn stars. Regions of dense gas and dust called nebulae are the birthplaces of stars. Within these clouds, gravity pulls material together until it ignites into new suns. Young stars are hot and blue. They illuminate their surroundings, creating spectacular glowing regions. Famous stellar nurseries include the Orion Nebula and the Eagle Nebula. Each contains hundreds of newly formed stars. The universe is still creating. Even now, new stars are being born across countless galaxies. Creation continues in the cosmic present. Magnetars can crack and release starquakes. Magnetars are neutron stars with extremely powerful magnetic fields. The fields are so strong they can deform the star's crust. Sometimes the crust cracks, releasing tremendous energy in an event called a starquake. A magnetar starquake on the other side of the galaxy can be detected on Earth. These events are brief but violent. They remind us that even stellar remnants can be active and dynamic. The universe is never truly quiet. The cosmic web was predicted before it was observed. Theoretical models of cosmic structure predicted that galaxies would cluster along filaments and around voids. When observations became detailed enough, we found exactly this pattern. The cosmic web was real. This is a triumph of science. Predictions made from theory, confirmed by observation. The universe behaves according to rules we can discover. This is profoundly reassuring. We can understand the cosmos because it is understandable. Space telescopes see what ground telescopes cannot. Earth's atmosphere blocks many wavelengths of light. It also blurs images with its turbulence. Space telescopes like Hubble and Webb orbit above the atmosphere, seeing clearly across the electromagnetic spectrum. They have revealed galaxies at the edge of the observable universe, detailed nebulae, and planets around other stars. By leaving Earth, we see the universe more clearly. The cosmos rewards those who reach for it. The universe is mostly empty space. If you could somehow remove all the empty space from atoms, all the matter in the observable universe would fit into a relatively small volume. Atoms are mostly empty. The nucleus is tiny compared to the electron cloud surrounding it. Stars are separated by light years of vacuum. Galaxies by millions of light years. The universe is vast, but its contents are sparse. We live in a cosmos that is mostly nothing, punctuated by occasional something. Dark energy may be a property of space itself. We do not know what dark energy is, but one possibility is that it is intrinsic to space. As space expands, more space is created, and more dark energy appears. This creates a feedback loop, accelerating expansion. If dark energy is a cosmological constant, built into the fabric of reality, it will continue driving expansion forever. The fate of the universe may be determined by a property of emptiness itself. Nothing may be the most powerful thing of all. Some particles move faster than light in certain media. Nothing can travel faster than light in a vacuum, but light slows down in materials like water or glass. In these media, particles can exceed the local speed of light, creating a shock wave of radiation called Cherenkov radiation. This blue glow is seen in nuclear reactors and particle physics experiments. The speed of light is the cosmic limit. But within materials, different rules apply. Physics has layers of subtlety. The universe has a shape, and we are trying to measure it. Space could be curved positively, like a sphere, negatively, like a saddle, or flat, like an infinite plane. Current observations suggest the universe is very close to flat, but small curvature is hard to detect. Measuring the shape of the universe requires precise observations of the cosmic microwave background and the distribution of galaxies. We live inside the thing we are trying to measure. This makes the task challenging, but not impossible. The shape of reality is within our grasp. Time dilation has been measured on Earth. Clocks at higher altitudes tick slightly faster than clocks at sea level because gravity is weaker there. This effect is tiny, but measurable with atomic clocks. GPS satellites must account for it to provide accurate positioning. Time is not absolute. It flows at different rates depending on gravity and motion. Einstein's predictions have been confirmed countless times. Relativity is real. The universe is stranger than common sense suggests. The universe contains magnetic fields on enormous scales. Galaxies have magnetic fields. So do galaxy clusters. Even the cosmic voids may contain extremely weak fields. These magnetic fields affect the motion of charged particles and the propagation of cosmic rays. We do not fully understand how such large-scale fields originated. They may trace back to the early universe. Magnetism is everywhere. From tiny atoms to the largest structures, fields thread through the cosmos. The observable universe contains more photons than atoms. For every atom in the universe, there are approximately 1 billion photons. Most of these are cosmic microwave background photons, the afterglow of the Big Bang. This ocean of light fills all of space. It bathes every corner of the cosmos in a faint, ancient glow. We swim in a sea of photons. They pass through us constantly, unnoticed, carrying information from the beginning of time. The universe is luminous in ways we cannot see with our eyes. It is filled with light beyond our perception. Pulsars are the most precise clocks in nature. Neutron stars that emit beams of radiation are called pulsars. As they spin, these beams sweep across space like lighthouse beacons. Some pulsars rotate hundreds of times per second with extraordinary regularity. Their pulses are more precise than atomic clocks. We use pulsars to detect gravitational waves, to test general relativity, and to navigate spacecraft. These dead stars, the remnants of cosmic explosions, have become our most reliable timekeepers. The universe creates instruments of precision from catastrophe. Stars can be born in pairs, triplets, or larger groups. Our Sun is a solitary star, but many stars have companions. Binary star systems are common. Triple and even higher order systems exist. These stellar families orbit each other in complex dances that can last for billions of years. When one star in a pair dies and becomes a white dwarf, a neutron star, or a black hole, dramatic interactions can occur. The universe creates families of stars. Some are peaceful, others are violent. All are fascinating. The cosmic microwave background has hot and cold spots. The CMB is not perfectly uniform. It contains tiny temperature variations, about 1 part in 100,000. These variations are the seeds of all cosmic structure. Regions that were slightly denser in the early universe became galaxies and clusters. By mapping these variations, we learn about the early universe and the physics that governed it. The pattern of spots in the CMB tells us about inflation, dark matter, and the geometry of space. Ancient heat variations have written the story of cosmic evolution. Neutrinos were produced in enormous numbers during the Big Bang. In the first seconds of the universe, neutrinos were created abundantly. Like the cosmic microwave background, these neutrinos still fill all of space. The cosmic neutrino background has never been directly detected because these neutrinos have so little energy and interact so weakly. But we know it exists. Theory demands it, and future experiments may finally detect it. The universe is filled with particles from its birth that we cannot yet see. Gravitational lensing reveals hidden matter. When light from a distant galaxy passes near a massive object, gravity bends its path. This effect, called gravitational lensing, can magnify and distort the images of background galaxies. We use lensing to measure the mass of galaxy clusters, to find dark matter, and to see galaxies too faint to observe directly. Light becomes a probe of mass. Gravity becomes a lens. The universe reveals its hidden structure. Some galaxies are falling toward us, while most galaxies are receding due to cosmic expansion. A few nearby galaxies are moving toward the Milky Way. The Andromeda Galaxy is approaching at several hundred kilometers per second. In about 4 billion years, it will collide with our galaxy. On local scales, gravity can overcome expansion. Galaxies can attract each other, merge, and form larger structures. The cosmic dance includes both expansion and attraction, both pushing apart and coming together. Brown dwarfs are failed stars. Not every collapsing cloud of gas becomes a star. If the mass is too small, nuclear fusion never ignites in the core. Brown dwarfs are objects between the largest planets and the smallest stars. They glow dimly from gravitational contraction, but do not fuse hydrogen. These failed stars are common in the galaxy. They float in the darkness, never achieving stellar radiance. The universe has gradations. Not everything that tries to become a star succeeds. Rogue planets wander between stars. Some planets are not bound to any star. They drift through interstellar space, alone and cold. These rogue planets may have been ejected from their birth systems by gravitational interactions. There may be billions of rogue planets in our galaxy alone, dark worlds wandering through the void. Not all worlds have suns. Some exist in perpetual night, warmed only by their own internal heat. The universe has gone through distinct eras. First came the radiation era, when photons dominated. Then the matter era, when atoms and gravity shaped structure. Now we are in the dark energy era, when the accelerating expansion dominates the dynamics. Each era has its own physics, its own character, its own story. The universe has chapters. We exist in one of them. Others lie behind us and ahead. Cosmic rays constantly bombard Earth. High-energy particles from space strike our atmosphere continuously. Most are protons or atomic nuclei, accelerated by supernovae or other energetic events. When cosmic rays hit air molecules, they create showers of secondary particles that rain down to Earth's surface. Some cosmic rays have energies far beyond what any human-made accelerator can produce. The universe sends us high-energy messengers. They carry information about the most violent processes in the cosmos. Some stars have planets made of diamond. Under extreme pressure, carbon can crystallize into diamond. Some exoplanets may be rich in carbon and experience pressures high enough for this transformation. These diamond planets would be unlike anything in our solar system. Harsh, dense, and glittering. We have not directly observed such a world, but theoretical models suggest they could exist. The universe creates wonders we can barely imagine. Cosmic strings may stretch across the universe. Some theories predict the existence of cosmic strings, ultra-thin defects in spacetime, left over from phase transitions in the early universe. If they exist, cosmic strings would be incredibly dense, thinner than an atom, but heavier than mountains. We have not detected cosmic strings, but their presence would create distinctive gravitational effects. The universe may contain structures unlike anything we have seen. Reality may be stranger than we know. The cosmological principle assumes the universe is uniform. Modern cosmology is built on this assumption, that the universe is homogeneous and isotropic on large scales. This means no location is special, and the universe looks the same in all directions, when viewed at sufficient scale. Observations largely support this principle, though some anomalies remain unexplained. We assume uniformity because it makes the mathematics tractable, and so far, the assumption works. The universe cooperates with our simplifications. Red giants are cooler than blue giants. Star color reveals temperature. Blue stars are the hottest, with surface temperatures exceeding 20,000 degrees. Red stars are cooler, often around 3,000 degrees. Our Sun is yellow, with a surface temperature of about 5,500 degrees. When you look at the night sky, the colors tell you the temperature of each star. Blue means hot. Red means cool. The universe is color-coded. Temperature is written in light. Black holes can spin at nearly the speed of light. When a rotating star collapses, it carries its angular momentum into the black hole. Some black holes spin so fast that their event horizons are dragged around with the rotation. This frame-dragging effect creates regions called ergospheres, where nothing can remain stationary. Energy can theoretically be extracted from a spinning black hole. The universe stores energy in rotation. Quasars are the brightest objects in the universe. Quasars are supermassive black holes actively consuming matter. The accretion process releases tremendous energy. A single quasar can outshine its entire host galaxy by a factor of 1,000. Quasars are visible across billions of light years. They illuminate the distant universe. The most energetic process in the cosmos involves matter falling into oblivion. The speed of gravity equals the speed of light. When gravitational waves from merging black holes and neutron stars were detected, scientists measured how fast gravity propagates. The answer matched the speed of light to extraordinary precision. gravity and light travel at the same cosmic speed limit. This confirms a key prediction of general relativity. Space-time ripples and light waves obey the same fundamental speed. The universe creates elements heavier than iron through special processes. Iron is the endpoint of normal stellar fusion. Heavier elements require different creation methods. Neutron star mergers produce rapid neutron capture, also called the R process, which creates gold, platinum, uranium, and other heavy elements. Supernova explosions also synthesize heavy elements through intense neutron bombardment. The precious metals on Earth were forged in the deaths of stars. Your jewelry was made in cosmic catastrophe. Baryon acoustic oscillations provide a cosmic ruler. Sound waves in the early universe left imprints in the distribution of galaxies. These baryon acoustic oscillations create a preferred scale. In the clustering of galaxies, a distance of about 500 million light-years. We use this scale to measure cosmic expansion and distance. The early universe left us measuring tools. We use them to map the cosmos. Science builds upon nature's gifts. The vacuum of space has energy. Even empty space contains energy. Quantum fluctuations give the vacuum a baseline energy level. This vacuum energy may be related to dark energy. It may be driving the accelerated expansion of the universe. Calculating vacuum energy from quantum mechanics gives a value wildly different from what we observe. This discrepancy is called the cosmological constant problem. We do not understand why the vacuum has the energy it has. It is one of the deepest puzzles in physics. Emptiness is not empty, and we do not understand why. The universe may be a hologram. Some theories suggest that all the information in a volume of space can be encoded on its boundary. This holographic principle implies that the three-dimensional universe we experience may be a projection of two-dimensional information. This idea arises from the study of black holes and string theory. It is speculative but intriguing. Reality may not be what it seems. The universe may be stranger than any science fiction. The multiverse remains a possibility. Some theories suggest our universe is one of many. An infinite number of universes may exist, each with different physical laws or initial conditions. The multiverse is not proven. It may never be provable if other universes are forever beyond our observation. But the mathematics of certain theories naturally produces multiple universes. The idea is taken seriously by many physicists. We may be one bubble in an infinite cosmic foam, or we may be all there is. We do not know. Light can push objects. Photons carry momentum. When light strikes an object, it transfers that momentum, creating a tiny push. This radiation pressure is too small to notice in daily life, but it matters in space. The tails of comets point away from the sun because solar radiation and wind push the dust and gas outward. Future spacecraft may use light sails, propelled by sunlight or lasers. to travel between stars. Light is not just information. It is also force. Antimatter is extraordinarily rare in the universe. For every billion particles of matter, there is virtually no antimatter left. Yet the Big Bang should have created equal amounts. Something broke the symmetry. Some process in the early universe favored matter over antimatter. We do not fully understand this asymmetry. It remains one of the great mysteries of cosmology. If matter and antimatter had been perfectly balanced, they would have annihilated completely, leaving only light. You exist because symmetry was broken. The universe is biased toward your existence. The cosmic web is still growing. Gravity continues to pull matter toward the filaments and nodes of the cosmic web. Galaxies are still falling into clusters. Clusters are still merging. The large-scale structure is still evolving. In the distant future, as dark energy dominates, this growth will slow and eventually stop. But for now, the universe is still building itself. Structure formation continues. Stellar winds shape nebulae and influence star formation. Massive stars emit powerful winds of charged particles that push against surrounding gas and dust. These winds carve out bubbles and sculpt the shapes of nebulae. When winds from multiple stars interact, they can trigger or suppress the formation of new stars. Stars do not exist in isolation. They interact with their environment, shaping and being shaped. Time began with the universe. There was no time before the Big Bang. Time itself came into existence at that moment. Asking what happened before is like asking what is north of the North Pole. The question assumes something that does not exist. Time is not a backdrop against which events occur. It is part of the universe itself. It is woven into space-time. It began when the cosmos began. This is difficult to imagine. Our brains evolved to understand time as a river flowing from past to future. But the river has a source, and the source is the beginning of everything. The future of the universe is unimaginably long. The universe is nearly 14 billion years old, but its future stretches far longer. In 100 trillion years, star formation will end. In 10 to the power of 40 years, protons may decay. In 10 to the power of 100 years, the last black holes will evaporate. These timescales are beyond comprehension. Our entire cosmic history is a single moment compared to what lies ahead. The universe is still young. Most of its history has not yet happened. We exist in the morning of cosmic time. The long afternoon and endless night are still to come. We are the universe becoming aware of itself. This is perhaps the most profound fact of all. The universe has existed for billions of years, but only recently has part of it begun to understand itself. You are made of atoms forged in stars. You are part of the cosmos. And you are thinking about the cosmos. The universe has grown eyes, ears, minds. Through you, and through all conscious beings. The cosmos contemplates itself. This is not poetry. It is physics. The atoms in your brain are the same atoms that formed in supernovae. The processes that allow thought are the same processes that govern stars. You are not separate from the universe. You are the universe. Briefly aware. And that awareness, however brief, is something extraordinary. Tonight, as you drift towards sleep, remember this. You are made of stardust. You exist in a cosmos that has been expanding for billions of years. Every atom in your body has a history, stretching back to the beginning of time. The universe is vast beyond comprehension. And yet here you are, breathing, thinking, resting. The stars will continue to burn. Galaxies will continue to drift. The cosmos will continue to expand. And somewhere within it all, on a small planet orbiting an ordinary star, you exist. There is no hurry, no test, no urgency. Just the quiet unfolding of existence. Just the slow passage of cosmic time. Let your thoughts grow soft. Let your breathing slow. Let the weight of the day dissolve, like starlight fading into the dawn. The universe will still be here when you wake. It has waited 14 billion years. It can wait a little longer. Sleep well. Sweet dreams. And may you carry with you, even faintly, the memory of a cosmos that holds you gently within its infinite arms. Thank you for joining me on this journey through the universe. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of the cosmos. There are more wonders waiting, more galaxies, more stars, more mysteries to drift through on quiet evenings. Rest well, and may the stars keep you company through the night. This has been Drowsy Discovery. Good night.